section. This is titled Rolle's Theorem, and then we'll discuss the mean value theorem. First, let me introduce to you Rolle's Theorem. And Rolle's Theorem says if f is a continuous function, remember what that means is that for every point within that interval, the function is defined. The limit exists for every point within that interval, and the limit value equals the function value. Now, a more basic way to think about it is you don't have to pick up your pen or pencil to draw the graph. That's a continuous function. On the other hand, differentiable means that when you take the derivative, we have a continuous function. In other words, it's differentiable for every single point between A and B. Notice the endpoints are not included because you're not necessarily differentiable at an endpoint. And finally, the third thing that must be true to be able to apply Rolle's theorem is that f of A must equal f of B. And if that's the case, all three of those things are true, then there is at least one number C in A and B such that the derivative, notice f prime of C, is equal to 0. So what I want to do is I have three graphs down here just for you to think about this. It says think of the many ways this could be depicted in graph form. So again, we have an interval A to B. That's where we have to start. Now, any function I draw must be continuous on AB. So when I draw this, I do not need to pick up my pen to draw it. It is defined at A and at B. Not only that, let me back up just a little bit. Okay, make sure you're clear on that. F of A must equal F of B. Okay, let me try that again. There's F of A equal to F of B. And when I draw my function, it needs to be continuous. And differentiable means it has no corners, right? No corners and no vertical tangent lines. So very similar to what I just drew. There we go. So that's an example of that. Now, this says there's at least one number C in between A and B such that f prime of C is equal to 0. Do you see where C might be located? The derivative is equal to 0. What is that really saying? It's saying the tangent line slope is equal to 0. And what I'm seeing is right here. I think that's a pretty good guesstimate of where you have a horizontal tangent line, which would make C right there. Okay? Think of the many ways that you could do this. See if you can trick yourself into disproving this theorem. Again, I set up A equals B. Okay? What if I just drew a horizontal line? Is there a point between A and B such that tangent line slope is equal to 0? Sure. Matter of fact, this is boring. Every point between A and B, the slope of the tangent line is equal to 0. So C could be any value up here. Any value, because the slope of the tangent line and the line are exactly the same. So that's a boring example, but it could happen. What if I draw some kind of super curvy line? Again, keep in mind A has to equal B. So I go down and I go up. Now that is a continuous function, you agree. It is differentiable because there's no corners or vertical tangent lines included in here. Can you find a value where the slope of the tangent line is 0? I can find two of them. Look, right here the slope of the tangent line is 0. And right here, the slope of the tangent line is 0. So this could be a C value, and this is another possible C value. I guarantee you there's no way you could connect the dots between A and B with a continuous differentiable function and not have a place where the slope of the tangent line is equal to 0. But the question is, do we really have to have a function that is both continuous and differentiable to set this up? And does f of A even have to equal to f of B? That's the question. So here I asked, do the following examples meet the criteria for Rolle's theorem? So let me draw an example. So here's A, and here is B. What if I draw this function here, and this is happening, and this is happening? Okay? Now, when I look at this, I don't see any place on this graph necessarily that has, maybe I need to redraw it just a little bit. That makes me feel better. I don't see anywhere on that graph necessarily that there is a horizontal tangent line. But the fact is I cannot use Rolle's theorem on this graph because it is not continuous. Okay. What I'm going to do is pause it for a minute and give you 2 more graphs so you can think about it, so you don't have to watch me draw it. All right, so next example, take a look at this one. I asked myself the conclusion, is there anywhere between A and B that has a horizontal tangent line? And you would tell me no. But the fact is, what's the problem with this? This function is not differentiable. Function that has a corner is not differentiable. The reason is, remember, the derivative is a limit value, okay? And it's the limit that gives you the slope. The slope over here is different than the slope over here. So right here, that function is not differentiable because you have a corner. Corners are not differentiable, but it's basically because those limits of the derivative, which is the slope of the tangent line, are not equal at all. So if it's not differentiable, you can't use Rolle's theorem. And not only that, if it's not differentiable, it is possible that you don't have a place that the derivative is equal to 0. And then this last example down here, look at this graph. I don't see anywhere there that you might have a horizontal tangent line. It looks like almost at this endpoint, okay, but we're talking about between A and B. There's no place with a horizontal tangent line. But the fact is, f of A is not equal to f of B, okay? And if you don't have all 3 of these conditions, then Rolle's theorem doesn't apply whatsoever. All right, so for our first example, this is an example of a problem that actually uses Rolle's theorem, but it doesn't say a word about Rolle's theorem. It says find 2 x-intercepts of the function. So the first thing we want to do is find x-intercepts, which is not a calculus thing to do, and show that f prime of x is equal to 0, that's definitely a calculus thing to do, at some point between the 2 x-intercepts. So let's just follow the steps, and then we'll see how Rolle's theorem may or may not apply to this problem. So first, find our 2 x-intercepts. Now you know how to find x-intercepts, don't you? So you set the equation equal to 0, or the function 0 equals x squared plus 6x. I need to factor. You could also use the quadratic formula if you really wanted to. X times x plus 6, and then I set each factor separately equal to 0. And then I get, of course, x equals 0, and x is equal to negative 6. All right? So I've got my 2 x-intercepts. Now what else does it say? It says find 2 x-intercepts of the function and show that f prime of x equals to 0 between the 2 x-intercepts. Now this is almost like dealing with our interval, right? So if we take a look at the interval 0 to negative 6, okay, we need to ask ourselves, does it meet the conditions of Rolle's theorem? Right? Is this function continuous? And I hope you will tell me yes, because it's a polynomial. Remember, all polynomials are continuous. We even proved that. Okay. Next, is it differentiable? All polynomials are differentiable. We proved that. We trying to remember if we proved that all polynomials are continuous. I think we did, but we definitely proved that all polynomials are differentiable. And then, does f of a or f of 0 equal f of negative 6? Well, sure it does, because they're both x-intercepts. You know what that means? If it meets those 3 conditions, we can use Rolle's theorem. Okay? So Rolle's theorem applies. Now, what does that mean? Rolle's theorem says, now let me flip back just so you can see this. Rolle's theorem says there is at least one number, C we'll call it, in the interval A to B, for us, that's 0 to 6, I can't remember, such that f prime of C is equal to 0. So it's saying there's a place between those 2 x-intercepts that the derivative is equal to 0. Negative 6. And look at that. I bet y'all caught this. Don't tell anybody you did this. I wrote the interval completely backwards. Ooh, what's happening now? I need to erase. Don't tell anybody. Okay, how about negative 6 to 0? Whew, okay, much better. So f of 0 equals f of negative 6 is continuous, it's differentiable, so let's use Rolle's theorem. Rolle's theorem says that if we take the derivative, so let's do that, f prime of x is equal to 2x plus 6, and I set that equal to 0. 0 equals 2x plus 6. When I solve that, it's going to be a number between negative 6 and 0. Okay, at least there's going to be a value between negative 6 and 0. So I subtract the 6, I divide by 2, and I get x is equal to negative 3. Is that between negative 6 and 0? Sure is. We were guaranteed the value. Okay, so find two x-intercepts of the function and show f prime of x equals 0 at some point between the two x-intercepts. Notice it didn't actually ask for what point. It just says show at some point. So when we said Rolle's theorem applies, then we showed at some point it's true. We actually found the point. So I think we kind of went above and beyond on this question. So question B, we want to determine whether Rolle's theorem may be applied on the closed interval AB. Find all values of C in the open interval such that f prime of C equals 0. By the way, folks, that's exactly what we did on the last problem. So we found the C value even though they didn't ask for it. So can we even use Rolle's theorem on this? Is this a continuous function? So you've got to check all three of those. Is it continuous? And you would tell me yes. Why do I know this is a continuous function? Because it's a polynomial, isn't it? It's factored out, but it's still a polynomial. So all polynomials are continuous, not only just between negative 2 and 4, but over the whole real number line. All polynomials, every single one of them. Now, if you're struggling with that, go back and look at the definition of a polynomial somewhere so you know what to recognize. You're talking no square roots, no radicals whatsoever, no negative exponents. That's a polynomial, and you're adding and subtracting. Next, is this function differentiable? And you were supposed to tell me, well, it certainly is. Why? Because it's a polynomial. Not only are polynomials differentiable between negative 2 and 4, but they're differentiable everywhere. Once again, how do you recognize a polynomial? Make sure you can do that. No absolute values, no radicals, no fractional exponents, no negative exponents, no x's in the denominator. Then you have a polynomial. Finally, is f of a equal to f of b? So this is the general way of saying it. For our problem, we're looking at negative 2 and 4. So is f of negative 2 equal to f of 4? Well, let's find out. We have to show it. So I've got negative 2 minus 4. I'm plugging into my function. Negative 2 plus 2 squared. What does that equal? 0. How did I know so fast? Right here. And when you multiply by 0, your answer is 0. Now I'll plug in 4. So 4 minus 4 times 4 plus 2 squared. Once again, that's 0. How do I know? 0. 0 times anything is 0. So it meets all three conditions. So that means that Rolle's theorem applies. We absolutely know between negative 2 and 4, there's going to be a value C such that derivative is equal to 0. So now we got to find it. So we have to take the derivative. How would you like to take this derivative? What I hope you're going to do is use the product rule. You could multiply x plus 2 twice, x plus 2 times, well, multiply it once, but x plus 2 times x plus 2 and expand it, and then distribute the x minus 4. Or you could just use the product rule and the chain rule right here. So I've got first times the derivative of the second, so x minus 4 times 2 times x plus 2 to the first. So that's first root of the second plus the second, x plus 2 squared times the derivative of the first, which is 1. Okay, maybe pause it and do that on your own so you can follow. All right, now, here's what I noticed. These two terms, and this is a term, and this is a term, right? They have an x plus 2 in common. I'm going to factor that out. Hey, they both have a 2 also, don't they? So first derivative of the second plus the second derivative of the first. No, they don't. That's a 1. I can't even read my own handwriting. There we go. So I have a common x plus 2. I'm going to factor out front. Now, if I pull out that x plus 2, that remains x, well, I mean 2 times x minus 4 inside. If I pull out one of those x plus 2s, I still have an x plus 2 times 1. I'm going to leave the 1 off. Going to simplify this a little more. This is x plus 2. Now, here I distribute because it's time to combine like terms. That's minus 8 plus x plus 2. Uh-oh. How about a bracket? There we go. So now I have x plus 2. And then 2x plus x is 3x. And negative 8 plus 2 is minus 6. And I have f prime of x. All right. Now I have 3x minus 6. I could factor that 3 out or not. Remember, your goal is to set this equal to 0 and solve. If you factor it out or not, you can get the solution. So I said x plus 2 equal to 0 and 3x minus 6 equal to 0. Here I get x is negative 2. Here I add the 6 and divide by 3 and I get x is positive 2. Okay. Now, negative 2, Rolle's theorem says on the open interval, look right here it says a C between A and B, between A and B. So when I go back and I'll look at our work right here, this value doesn't really count because that's not between negative 2 and 4. This guy right here, that's our winner. That is between negative 2 and 4. Okay? So our answer is C equals 2. So question C, very similar. Determine whether Rolle's theorem may be applied on the closed interval AB. Find all values of C in the open interval AB such that f prime of C is equal to 0. So just like the last problem, but we just have an entirely different function, don't we? All right, so here we go. First thing, is this a continuous function? Now, this is not a polynomial, folks. So you would have to prove that this is a continuous function. How would you go about doing that? Okay, well, you would have to say, is it defined on the interval 0 to 6? Can I plug in every number between 0 and 6? And it is. Okay, there's nowhere we get undefined. And the next thing, does the limit exist? If I take the limit as x goes to some number between 0 and 6, can we do that? And that's just a substitution problem. You can take the limit of that without any issues whatsoever. So the limit exists. And finally, does the limit value equal the function value? And it does, because to find the limit, all you're going to do is plug in the number anyway. Okay? Another way, I know that that's not very satisfying. Another way to think about this is to graph it. If you look at the graph, y'all know that the absolute value is a V-shaped graph when it's next to the first inside. I like to call that a linear absolute value. But we're used to looking at it like this. Negative absolute value of x minus 3 plus 3 on the outside. That's been moved right 3 up 3. Like that. There's my corner. And it's been flipped upside down. So basically, this graph looks like that. Rough sketch. Now, is that continuous? Yes, I know you can clearly see it. Now, my next issue, I need to check. So it's definitely continuous. Is this function differentiable? Now, all we really care about is between 0 and 6. So between here and if we plug 6 into this function here. Okay? So I'm highlighting, there's my graph between 0 and 6. Is it differentiable? What would you say? I'm hoping you would say, no, it's not differentiable. Why is it not differentiable? That guy right there. Corners. We can't have any corners. Now, to truly prove it, y'all, what you would need to do is take the derivative at x is equal to 3. That's where our problem is, at the point 3, 3. And you would find that the slope of the tangent line over here is some positive value, positive 1, by the way. And the slope of the tangent line here is negative 1. Therefore, it's not differentiable right there. But if you can let me know it has a corner, I'm okay with that. That means it's not differentiable. What does that really mean? Ultimately, we cannot use Rolle's theorem. So we're dead in the water right there. We cannot go any further and use Rolle's theorem. Are you tired of these yet? D. Determine whether Rolle's theorem may be applied on the closed interval AB. Find all values in C on the open interval a, b, such that f prime of c is equal to 0. Okay, so have to throw in a trig function, right? Now, you got to check those three things. Is this function continuous? You know what this function looks like, right? You can plug in anything you want into cosine of x, and so it goes like that forever in both directions. So yes, this function is continuous. Is it differentiable? Okay. Now, one way is you can say, hey, that's a nice smooth curve. Smooth is, by the way, a definition in math. And if a function is continuous and differentiable, it's smooth. So I'm kind of saying it's smooth to answer the question, is it differentiable? That's not the right thing to do. Can we take the derivative? Well, we could check it out, right? F prime of x, the derivative of cosine, you know, is negative sine of x. And then you ask yourself, is that continuous? Because if the derivative is continuous, it's differentiable. Yeah, that is continuous because it's the same wave, just in a different place, right? So it is definitely a differentiable function. Then don't forget to check, is f of a equal to f of b? So our interval is 0 to pi. So I'm finding cosine of 0 and cosine of, that's a 0, and cosine of pi. Cosine of 0, y'all, is 1, right? Unit circle, angle 0 is right here. Cosine is the x value, that's 1. Cosine of pi, what's the x value over there? Negative 1. So f of a is not equal to f of b. Therefore, we cannot use Rolle's theorem. All right, I got one more of these. Then we can move on. At least I didn't change the function value on you. I just changed the interval. You notice that? So we already know this guy is continuous because we talked about it. Cosine is defined everywhere. We know it's differentiable. You know why? Because we took the derivative, and the derivative is continuous. It's defined everywhere, so it's differentiable. We'd already talked about that. Now, does f of a equal f of b? Okay, so f of 0 is cosine of 0. That was 1, just like it was a minute ago. And f of 2 pi is cosine of 2 pi. And you know that's also 1, right? Because the angle 0 and the angle 2 pi are coterminal. They land in the same place. So here's what we know. We know that if we take the derivative of this function, let's do it. So f prime of x is equal to negative sine of x. That means Rolle's theorem says that somewhere between 0 and 2 pi, that's equal to 0. So I set that equal to 0, negative sine of x. I solve the equation by dividing both sides by negative 1. So I'm solving 0 equals sine of x. Now ask yourself, on the unit circle, sine is a y value. Where is sine equal to 0? Now where is sine equal to 0? Well, it happens right here. Okay, and it also happens right here. So at x is equal to 0, at x is equal to pi, and it continues around at x is equal to 2 pi, at x is equal to 3 pi. It goes in that pattern, but we only care about the answers that are on 0 to 2 pi, and it's just that guy right there. X is equal to pi is our answer. Now, do you need to see that on the graph? What does cosine of x look like? Remember, cosine starts off the axis up here at 1. And down here, here's negative 1. And you could put key points like 0, pi over 2, pi, 3 pi over 2, and 2 pi. It repeats every 2 pi. Remember, so it's here, crosses, back up. That's what it looks like. And is there anywhere between 0 and 2 pi that you have a horizontal tangent line? Sure is. Like right there, right? And that's that pi value that we found. Alright, let's talk about something else. So I have a new theorem for you. There's only 2 theorems in this section, Rolle's theorem and the mean value theorem. And the mean value theorem is almost identical to Rolle's theorem except for one thing. Let's find it. So it says f has got to be continuous. We already know what that means, right? F has got to be differentiable. That means you can take the derivative and it's defined everywhere. We've already been checking those 2 things on Rolle's theorem. But there is no statement about f of a equals f of b. Okay, so keep that in mind. F of a does not have to equal f of b for the mean value theorem. But it says there exists a number in C, so between a and b, such that the derivative f prime of c is equal to f of b minus f of a over b minus a. Wow, what in the world is that saying? You want to see? Let's draw a picture. Okay, so here's a and here's b. Now my setup is f of a could equal f of b. That would just take you back to the more simplistic Rolle's theorem. So it doesn't have to be. So here, let's just put f of a right here, okay, and then f of b up here. Now, when I connect these two guys, I have to make sure I use a continuous function and a differentiable function. So no corners, no vertical tangent lines, nothing like that. So I'm going to keep it simple, and I'm just going to do an arc like that. Okay? Now, what is this business right here? F of b minus f of a over b minus a. Does that make you think of slope? It should. Y2 minus y1 over x2 minus x1. And it's the slope between a and b. So in red, the slope between a and b is whatever slope that red line is, right? I just connected the dots a and b. Well, what the mean value theorem says is there's somewhere between a and b that the tangent line has that very same slope. So watch this. What color do you want me to use? Purple? All right, purple it is. So check it out. I'm guesstimating it's about right here. Look. The slope of the tangent line is the same as the slope between a and b. And maybe I'm off a little bit, but you can see how it must exist in that picture, right? Another way I could do that, I could make it curvier, although my outcome picture is going to look a little bit messier. So bear with me. So here's A, and here's B. And let's this time let A be way up here, and B be way down here. Now let's connect the dots between these two. So something curvy like that, right? Now, first of all, my f of b minus f of a over b minus a, I'm going to do that in red. So when I connect those dots, my dog Beeford, he's pitching a fit again, I'm sorry. So when I connect those dots, it looks like that. Now, do you see somewhere along this curve that would have the same slope of the tangent line? So if I go back to my purple, and I draw, how about right here? Don't you think right here would maybe have the tangent line the same? Is that the only place? What if I drew another one in green? So I got some weirdness on my curve going on over here, but I'm thinking, oh, about here-ish. Maybe that would have. I didn't draw it very parallel, but maybe that line might be parallel. But the point is, you see that exists. I'm not saying it's exactly there. This would have two places. So if I look back at my first picture, my C value that they're speaking of would be there. In my second picture, it looks like we'd have two different C values. The one for my green graph there, and then one for my purple graph there. So it's kind of fun, isn't it? So I don't have too many of these problems for you to do. We spent a lot of time talking about continuous and differentiable and checking that, so I didn't want to do 5 of these for you as well, but I do want to show you a couple of them. So it says determine whether the mean value theorem may be applied on the closed interval AB, and if yes, then find all values of C in the open interval such that f prime of C equals f of B minus f of A over B minus A. So first of all, again, are we dealing with a continuous function? So are we dealing with a continuous function? I'm hoping you're going to say yes, absolutely we are dealing with a continuous function. Why? Because it's a polynomial. Not only are polynomials continuous on the interval 0, 6 that they gave us, but they're continuous everywhere. Same goes for differentiable. So when you see a polynomial dealing with Rolle's theorem or the mean value theorem, is easy because you know right off the bat they are continuous and differentiable. Why? Because, once again, it's a polynomial. Now, unlike Rolle's theorem, remember, you don't have to check to see if f of a equals f of b. If it did, then you would just be using Rolle's theorem and not the mean value theorem, because they say the same thing. Rolle's theorem is just a sub-theorem of the mean value theorem, actually. This is a special case. Okay, now, next. 2 things we got to find, right? 3 things, sort of. You've got to find f of b minus f of a over b minus a. And you've got to find the derivative, and then you've got to set the derivative equal to f of b minus f of a over b minus a. So first of all, let's do f of b minus f of a over b minus a. So, what? Ugh, irritating dog. So what we're doing, hush. So what we're doing is we're trying to find the slope of this line right here. Okay, our graph doesn't look like that, but we're trying to find the slope of that line. So when I do that, f of b, so I've got, what's b anyway? Well, it's 6, right? And a is 0. So when I find f of those, I need to plug 6 into my function. So that's going to be 2 times 6 to the third minus, and now f of a, 2 times 0 to the third over b minus a, so it's 6 minus 0. Continue to simplify. And I calculate 6 to the third and multiply it by 2. I get 432 minus 0 to the third, 0 times 2, 0, over 6 minus 0 is 6. Does 432 divided by 6? It does 72 times. So that is the slope. It's pretty steep. If I were to graph this, then we would have a very steep line between 0 and 6, those points plotted. Okay? Now, I've got this part handled. Now I want to move to the left side. I want to find f prime of c. Easy. Well, f prime of x first. So what is f prime of x? I just take the derivative of my function. So I'm using the power rule, scalar multiple rule. 3 times 2 is 6, and that'll be x squared. Now to find c, that's my last step. I've done the right, I've done the left, no particular order. I set them equal to each other. So I set 72 equal to the derivative and solve that equation. Okay, so I have 6x squared is equal to 72. Divide both sides by 6 to get 12. Okay, and then I take the square root of both sides. Don't worry, it's okay if you don't get a nice whole number. So I have the square root of x squared is equal to plus or minus the square root of 12. So x is plus or minus the square root of 12 simplified. Remember, you can bring the square root of 4 out, make it 2. 2 square root of 3. Now, think about your interval. What's c in this particular problem? Well, it's those answers, yet we're only talking about between 0 and 6. So the negative one doesn't apply, only the positive one. So c is equal to 2 square root of 3, okay? So no negative. Why? Because it's not on the interval from 0 to 6. It's not that it's a bad answer, it's just not on the interval from 0 to 6. Is 2 square root of 3 on the interval from 0 to 6? How big is 2 square root of 3? So if you multiply 2 times the square root of 3, I get 3.464. That is definitely between 0 and 6. So there you go. Hey, one more thing I want to point out. This is c is just an x value, right? If you wanted to know the point where this happens, you would have to take that c value or that x value and plug it into your original function to find the y. But it doesn't ask for the point. It just asks for the c value, which is really just the x value between 0 and 6 that makes that true. But if you ever want to know exactly where it is on the graph, then you would have to take that and find the point, in other words, the y value that goes with that. So for our last problem, we want to determine whether the mean value theorem may be applied on the closed interval AB, and then if yes, once again, find all values of c in the open interval such that f prime of c equals f of b minus f of a over b minus a. So remind ourselves, what do you have to check for the mean value theorem? Well, first you have to determine, is this function continuous? Now, you could go back to your notes or your chapter when we talked about continuity, and we know radicals are continuous on their domain. So really, we need to look at the domain of this function. And if you'll recall, to find the domain of an even radical, you set what's underneath to greater than or equal to 0 and solve. So 2 is greater than or equal to x. Another way to say that is the domain is negative infinity And I need a parenthesis there, not a bracket. There we go. Negative infinity all the way up to the biggest number the value can be is 2. Now notice our interval includes, or is a subset of negative infinity to 2. So we can say it's continuous because we know the domain and we know radicals are continuous on their domain. Now, is this function differentiable? Well, to really determine if a function is differentiable, you need to take the derivative. So let's do that. F prime of x equals. Now maybe before I take this derivative, we need to rewrite this function. So above it here, how about f of x is equal to 2 minus x to the 1/2 power. So I'll write that radical form in rational exponent form. So I'm going to use the chain rule. So a power rule within the chain rule, 1/2 comes in front. Rewrite the inside of your function, 2 minus x. Reduce that power by 1, so 1/2 minus 1 is negative 1/2. But don't forget times the derivative of the inside. Now next, I just want to simplify it, because to really discuss it, it would help to simplify it. So that negative 1/2, I'm going to take it to the denominator. You've got 1 times negative 1 that remains in the numerator. That 2 is in the denominator, and again, that's 2 minus x now to the positive 1/2. So our final simplified result is negative 1 over 2, and that 1/2 is really a square root. Now feel free to go from there to there in one swoop. I just wanted everybody to see the steps involved. Now, I squared it off so we can find it later. It certainly doesn't answer this question, but that's our derivative. Now, where is this function continuous? Okay, well, we've got a denominator, right? And the denominator is not allowed to be 0. So if I substitute in 2 at x equals 2, we have a problem. But remember, when we're talking about differentiable, we're talking about over the open interval, -7 to 2, not the closed interval. So 2 really doesn't matter. 2 is not an issue. What about the numbers -7 to 2? Is this defined between -7 to 2? Well, sure it is. It's not going to give you a 0 on the denominator. It's not going to give you a square root. So this function is differentiable on -7 to 2. So now that we have that, we know we can use mean value theorem. So what is the next step? I go ahead and find f of b minus f of a over b minus a. How do I do that? First of all, what's b and a? So a is -7 and b is 2. So when I substitute in f of 2, so that's going to be plugged into my function, that'd be the square root of 2 minus 2, minus f of a would be the square root of 2 minus a -7 over b minus a. So b is 2 minus -7. And I simplify that. It's going to give me the square root of 0 minus the square root of 9 over 2 minus 7 is 9. That's going to give me negative square root of 9 over 9, which is -3 over 9, which is -1/3. So that's my f of b minus f of a. Again, I'm squaring it off, not because it's my answer at all, but I need to find it. Now the last remaining step is to set the derivative equal to f of b minus f of a over b minus a and solve. And that's going to find your c value. We've already taken the derivative, so that's helpful. Let's change colors. So we go red, -1 over 2 square root of 2 minus x is equal to -1/3. So we're solving this equation. A couple ways you can handle it. You can multiply both sides by the denominator, or you could just make your life easy and cross multiply real quick. So when I cross this way, I've got -2 square root of 2 minus x is equal to, when I cross this way, -3. Now remember, I'm trying to solve for x, so I'm going to divide both sides by -2. That's going to give me the square root of 2 minus x is equal to -3 over -2, which is really the square root of 2 minus x is equal to 3/2. Now I square both sides to get rid of that square root. It's going to give me 2 minus x is equal to 3/2 squared, which is 9/4. Now, I need to solve for x, so I'm going to subtract 2 over. So it's going to give me -x, and when I subtract 2, that's 9/4 minus 2, That would give me negative x is equal to 9/4 minus 8/4, common denominator. Negative x is equal to 9 minus 8 is 1/4. Finally, get rid of that negative by dividing both sides by -1, and that gives me x is -1/4. Now, what is that really? That is my c value. So right here, my c value is -1/4. Now, you always check to make sure that value is within your interval. And -1/4 does live between -7 and 2. If we graph this, we could probably see what's going on as far as the slope of the tangent line. You want to take a look at that? Let's do it. Okay, so I've gone in Desmos, and if you'll notice, over to the left, I've graphed y equals the square root of 2 minus x. And we all know that's the square root, so it's an arc over graph. Notice the domain, -infinity to 2. We're only looking between -7, which is right out here. Okay, it's moving the graph around, I'm sorry, all the way to 2. I also plotted the point. We found the c value was -1/4. Now imagine, if you will, because I can't write on this graph in Desmos, but connecting the point right down here at 2, 0 with the point right over here, which looks like -7, 3. If you connect that line, if you'll notice, that line connected, and I'm trying to draw it out, would be parallel with the tangent line that we've got drawn right there. Okay, you see that? So again, imagine drawing a line, a straight line from 2 way up here to -7, 3, connecting the dots, and then the line at the point, the c value that we found would be parallel to that line. In other words, they have the same slope. So I hope that helps you out. As always, let me know if you have questions, and have a great day.